Shall we start now?
Yes, sir. Welcome back, sir. Welcome, participant. Day 2, session 2. It is the topic of the session is multiple regression in finance. Over to you, sir. Prabhat, sir.
Yeah, sure.
Okay.
So if you can unshare.
Yeah.
All right. So I'm going to start with another set of data. So let me just fetch the data for you. And then we'll move to regression after this analysis. So this data is about the grocery shop where you have the store ID, means different places where the stores are located. This is health food kept in the store or not, the size of the store, organization kind, type, uh, customer ID, gender, shopping for, veg, non-veg, shopping style of the customer, are they using the coupon or not, and the amount they spent when they come to purchase. So I'm going to use Anova and Ancova model just to model the amount spent by the customer. So just to give you an idea about how Anova and Ancova works, and after that we'll move to regression. So here in Anova model, we need to actually be sure that the dependent variable you're looking for is a quantitative variable, that is a scale variable. So here the amount spent is in numbers, in rupees. So this is a scale variable. So we can actually do, and the independent variables can be a categorical variables like gender. You want to model gender on the basis of, we want to take the gender as a factor for analyzing the purchase, or maybe any other factor which is a categorical variable. So here the case is that we have the dependent variable. The variable which we are trying to model is a scale variable, and the basis on which we want to model this are the categorical variables. So that's the case of Ancova. So we go to analyze, we go to general linear model. So it falls under the general linear model, and we'll go to univariate analysis first. And this is the window that will appear. So it's asking which is the dependent variable. So we'll say, okay, amount spent is dependent variable. So it has to be a scale variable. Then what are your fixed factor based on which you want to explain? So I'm going to take, let's say, gender as one factor to explain it, and probably shopping style, another factor, which I'm going to consider for analyzing the amount spent. So this is a simple Anova model. So where we have the two independent variable and one dependent. And we are taking two independent variable, and there is something called the interactive effect, which we are going to also enshrine into the model. So what is interactive effect? Interactive effect means when you're looking at the impact of gender on purchase, that is univariate, or it is not an interactive. And when you're looking at shopping style and purchase, so if a particular person comes as a weekly buyer or a monthly buyer, these are the shopping style. How do they affect the purchase? So again, you are going for univariate or one single variable model. But if you want to look at the impact of gender versus shopping style, or maybe gender vis-a-vis shopping style, that means one who is going for weekly purchase, if it is a female or if it is a male, and one who is going for, let's say, monthly purchase, if it is a female or a male, how does that affect the purchase. So these are wonderful, beautiful style, analysis that we can do. So it's a full factorial model. So we'll say, okay, uh, contrast, we are going to create the, let's see if there are any contrast that we can create. So we are not looking for any contrast. We can say, okay, we'll go to the plot. So yes, we do like to have a plot. So it helps us. So we'll say separate the line based on gender and give us the horizontal line axis as the style and add it. So gender and style interaction that will be there. So we'll say okay. Then we go to post hoc analysis. Post hoc analysis is about the fact that it's based on the assumption. The whole analysis is based on the assumption that data variation has equal variance, and these are the tests which are designed for measuring whether they have equal variance or they don't have equal variance. So and you can pick up any of these. So generally we go for the test called LSD, which is one of the robust tests, or Tukey is also based on some robustness of the test. So this is the test that we have to, and then we'll say save. We'll say okay, I don't want to save anything. Options. If you want to have mean value for these three, you can actually look at the mean values, and some of these also you want to calculate. You can calculate. These are the diagnostic one. So maybe descriptive and statistics is going to help. Homogeneity test you can take, or the variance. These are the diagnostic parts, so we can deal with that later. First, we understand how it works, how it looks like. So this is the between the factors, subject factors. So we have the two factors. We have taken the gender, male, female, and the shopping style. There are three shopping styles. One is bi-weekly, similar items, and weekly bulk items, and often what is on sale. So bi-weekly customers are the one who look for the similar items. Those who have purchased last week, they will also look for a similar item this week. Weekly customers are looking for the bulk purchase, and customers who are guided by some kind of like coupon or discount, they are going to come as a often customer. So what's on sale? So they are more propelled by the sales factor. So here the descriptive statistics in front of you. These are the mean sales, male wise, male bi-weekly, weekly, and often, female bi-weekly, weekly, and often. So if you compare these means are different, and it seemingly looks like that the male actually spends more than the female when they come for the purchase. And these are the standard deviations. So one of the assumption of this ANOVA model is that these standard deviations are insignificant. They are not significant deviations. If you look at the test of the effect, here we find that the gender is significant because the p-value is 0.000. That means the sale, the gender effect on the sale is significant. Style is not significant. So it doesn't matter whether the purchaser are weekly or bi-weekly or often. It doesn't make much sense because it's not significant. But the interactive effect of gender versus style is significant. So when we start looking at the style of purchase vis-a-vis gender, then it becomes significant. So that's the beauty of this analysis. The rest of the estimations are about the marginal means. Marginal means are about the fact that if there is a additional change in this variable, for example, additional male enters into the store or additional female enters into the store, what is going to be the average impact on the sale? So that is the measurement. So it helps us in predictions also. So these are also given for the gender shopping style interactions. This graph is very interesting in ANOVA model, which tells us the blue graph is male and the and the green graph you can see is the female. And if you look at the bi-weekly similar item purchaser, the female purchase is far less than the male purchase. So if it is a bi-weekly purchaser, the male bi-weekly purchaser will buy more than the female. And the male weekly purchaser, if it is male, is also again going to purchase more than the female. But on the often customers, they are almost the same. So male and female, they behave the same way. But if you look at the marginal change in the behavior from weekly to often, then the male actually curve is going down, and while the female's curve is going up. So this means that if you want to make female purchase more in your store, then you need to give a lot of discount and sales to them. So they'll be more attracted towards sale items or often items, discounted items. So if you send the discounting coupon, if you want to send through mail and etc., don't send it to male, because they are not going to use it more. Send it to female, they are going to use it more, right? So something of this sort. So these graphs are very important, and they give us a lot of insight. So this is how the ANOVA model works. Then if you want to go to the same model and then try to add some covariate into it, like the geography, how the geography plays. So store ID represents the geography. So we can also look at the impact of covariate geography as a covariate. So does it make a difference if the store is located nearby the home or far away from the home? Does it affect the purchase? Or another way is to look at who's shopping for whom the shopping is being made. Does that also affect the customer? Let's take who's shopping for as a covariate, and then we'll say okay, with a similar kind of analysis. And if you go to the main table to look at how it has affected the result, so in this table we can see that who's shopping for is significant, gender is significant, style is also significant in their own way. In the previous analysis, when the covariate was not used, it was found that the style was not significant per se. Gender was significant, but the interactive effect of gender and style was significant. And here also, it remains to be significant. But all the other factors are becoming significant when we use the covariate. How does it affect the graph? The essence of the graph remains the same, that average expenditure by the male is higher than the average expenditure done by the female. But the direction of purchase is also the same. Like a male who is given more or attracted as a more often customer by throwing some sales items or all, and like that, they are not very much attracted, because the more sales you throw to them, the lesser they purchase. But more sales you throw to female, the higher they purchase. So something of this sort. So if you really want to attract a male customer, then you also need to look at what are the things that they have purchased last time. So if you have the account of those things which they purchased last time, and if they visit the store again, they are more likely to purchase the same item next time. So and they are also very much inclined to purchase from a particular place. So it also has implication for how you keep and where you keep that product. Say for example, if a male enters the store and takes the right turn and then takes the left turn and pick up a particular product, let's say shaving cream from a particular stack. And next time he comes, he again enters the store, takes the right turn and take the left turn. And if he doesn't find the shaving cream over there available, because the store has been rearranged and changed, the product has been changed to a different place, you are more likely to see a scenario where this person will end up spending less. So he will rather not purchase, rather than going for searching where this product is actually kept. So something of this sort. So there is a lot of insight that can be done. So this is ANOVA model and ANCOVA model. So any question on that? So if this is fine, then we can move to regression, which is our main preoccupation. We need to learn a little more on
So
regression.
there are questions in the chat box.
Yeah, okay, please read that
Uh,
on.
So there is a question that Namika Madam has asked, how can we measure the trust?
How can we measure trust?
Yeah.
All right, so good question, but there are many attributes which are not measurable. Trust is one of them. So if you really want to measure any variable which is not measurable, then you need to understand what, first you have to define what does that mean. So you can actually decipher and tell what do you mean by trust. Uh, and if a person has trust, how do you want this person to act or behave? Say, for example, the first thing that you can identify is that if a person has trust, this means he will listen very carefully. So he will have a listening capability. So this is one parameter you have identified for explaining trust. Then you say, okay, so this person will also, uh, you know, will listen and also comply. So whatever you say, he will comply. Second, third, you say, okay, he will follow timeliness and he will not bunk. So if he is a trustworthy person. So third characteristics. Fourth, uh, he may have compassion, a lot of compassion, and he will considerate uh, in dealing with people. So that's the fourth. So likewise, if you have actually identified 4 or 5 dimensions which actually go on to contribute to trust, now on these 4 or 5 dimensions, you have collected the data because these are the measurables. You can ask these questions to people. How do you rate yourself on listening from 1 to 10, let's say, or 1 to 5, let's say? Then you can ask people, how how often do you follow what you say, right? Say, for example, if your friend has asked you to come at around 5 uh, and meet at some place, do you how often do you are you prone to come on time over there? So something of this sort. I'm just guessing some of these. So likewise, you
Sir,
keep on asking questions. Yeah, Namika.
so like I want to find out some purchase intention to a trust,
Hmm.
like trust and purchase intention of consumer. अगर कंज्यूमर ट्रस्ट करता है तो परचेज उसके परचेज इंटेंशन डेवलप होती है, ठीक
Okay.
है? तो अगर मेरे सारे क्वेश्चन अगर लिकर्ट स्केल पे, तो इज इट राइट लिकर्ट स्केल पे? अगर समवन सपोज देयर इज अ वन क्वेश्चन दैट आई ट्रस्ट द ऑर्गेनिक सर्टिफिकेशन लोगो ऑन ऑर्गेनिक फूड प्रोडक्ट लेवल, or
Hmm.
I trust the information on organic product level.
Hmm.
Or another question is I'm willing to buy this organic product in the future.
Hmm.
तो सर इसको मैं आपका लिकर्ट स्केल पे इसको डाल के क्वेश्चनर अगर मैंने बनाया है, तो सर ये मेरा ऑब्जेक्टिव क्लियर होता है अगर मैं परचेज इंटेंशन करना चाहती हूँ कि हाँ ट्रस्ट का इम्पैक्ट होता है परचेज इंटेंशन पे? अगर कंज्यूमर ट्रस्ट करता है ऑर्गेनिक फूड पे तब वो परचेज करता है.
Yeah, absolutely. Bilkul. So you are absolutely right. And my suggestion would be that you go ahead with the Likert scale, though it has limitations, but uh, because your research is going to be comparable to the similarly done research elsewhere, because most of them are
Yes.
using Likert scale. So you can do that. And you can
तो
go
सर
ahead.
मैं
And
ओके सर वन मोर क्वेश्चन कि सर ये जो हमारा ट्रस्ट है तो इसको मैं मेजर करने के लिए, जैसे आपने अनोवा बताया, टाई स्क्वायर बताया, तो मुझे थोड़ा कंफ्यूजन है कि मैं कौन सा टूल अप्लाई करूंगी इसको मैं
so
कैलकुलेट
you
करने
have
के
to
लिए
use
या
the factor.
एनालिसिस करने
You have to first do the factor analysis,
के
because these are the measurement which you cannot do from any other. Because suppose कि आपने trust के लिए 5 factors बनाए और 5 questions बनाए
जी
जो कि trust को
जी
दिखाता है,
सर,
right?
यस सर,
आपने उनसे पूछा कि भाई आप ब्रांड को कैसे व्यू करते हो, डू यू रियली ट्रस्ट दिस ब्रांड और नॉट, डू यू रियली, गिवन एन अपॉर्चुनिटी वुड यू परचेज दिस, given an opportunity would you recommend it to your friend, given an opportunity would you use it for your children, something like that. So these are the trust factors. ठीक है, तो आपने 5-7 बना लिए. अब क्वेश्चन ये है कि now these, you are assuming that these 5-7 actually go on to explain trust, right? But statistically speaking, whether these questions are 100% contributing to the trust or not, that's first. Second is whether the questions are not overlapping. That means one question is explaining a part of trust, another question is explaining the same part of the trust. That means there is overlapping on same thing has been explained by 2 questions. So your questions have to be different. So the part which is explained by one question should not be explained by the other question, right? So then it makes into a good statistical analysis. So you have to remove those redundancies. So you can remove those redundancy only through a factor analysis, right? Without factor analysis, you cannot do that. So factor analysis is the best way. And after factor analysis, you come to understand whether these 5 factors actually, how much they are contributing to trust analysis. Maybe it is 60% they are explaining to the trust, or 70% they are explaining to the trust, something of this sort. So you look at the eigenvalue and the percentage that it explains. So that gives you the
eigen.
Yeah.
Okay, sir. Thank you, sir.
Yeah, absolutely. So let's move forward. We are now going to talk about regression. So here is the regression model in front of you. So we have this linear regression equation in front of you. So when we write y is equal to beta 0 plus beta 1 x, the caps which are given is called the estimated figure, because we are estimating the regression from the sample data. So these are the estimated figures. So we'll have to actually go for the hypothesis testing, and then only you can confirm that these figures are there for the population. So that's why this the estimated is put on the parameters. So y is equal to beta 0 plus beta 1x, and beta 0 is your intercept, the beta 1 is your slope. But this is called the mathematical model. The second model, if you look at, is y is equal to beta 0 plus beta 1x plus e, and e is called the error factor, error term, or the random factor. So and this model is called the statistical model. So what we actually measure in social science is the statistical model and not the mathematical model. So the difference between mathematical model and statistical model is this factor e. And what does it say? It says that in mathematical model, the conceptualization here is that the y is a function of x. In this equation, the first equation, if you look at, the conceptualization is the y is a function of x. And what it says is that the y, any change in y is actually coming from the change in x. So when x changes, the y changes, and 100% change that we see in y is coming from the change in x. There is no other factor which is affecting the change in y or causing the change in y. That's what the mathematical model says. So it's very exact. This model is exact. So in social science, there is nothing called exact models. The models are always inexact because we don't know which other factors are affecting the dependent variable. So here in the second model, if you see, it is saying that the change that is occurring in y is causing by the change in x, and also causing by the change in other factors which we are not very sure of or not aware of. And that's what the purpose of model is. Because when you prepare a model like this, you consider all those possible factors based on your theory, your understanding, knowledge. You add on the right-hand side all those possible factors which you think that is going to affect y, right? But after having done that, even after that, there may be some factor which might affect y which you are not sure of or you are not aware of. And these are clubbed under the error term. So, that is what this random factor, the error factor is all about, right? So we actually measure the statistical model, not the mathematical model. So here the beta 0 is the minimum value of y when x is 0, and it's also called the intercept. So when the dependent variable is put to 0, let's say, so if you put x is equal to 0, then what will be the value of y? The value of y will be equal to whatever is the intercept over here, and that's why it is called the intercept. The beta 1 is the rate at which the y will change or increase when the x increases by a given unit. So in this equation, if you look at all these kind of graph, so here the curve is originating from this place, and from the distance between 0 to this place is the value of beta 0. So the originating point of the curve is the intercept, and the way it is getting the slope, like upward sloping or downward sloping or straight line in the third graph, these are all indicator of the slope. So in the first graph, the upward sloping curve has a positive slope,
shape,
positive slope, and downward sloping curve has a negative slope. And if it is parallel to x-axis, it has no slope. So beta is equal to 0. The beta 1 is equal to 0. So these are some of the formulations of the graph, right? So that's what the regression line looks like, which is a regression line, which is a simple, single equation regression. We call it simple equation. And if on the right hand side, if you're using more than one factor, then it becomes a multiple regression. So right now we are dealing with a simple regression with one single variable, right? And these are the explanations of different betas and all, right? So here you see the change. What we are interested in knowing how the change in y is occurring and how much it is explained by the factor that we have considered, that is x, and how much it is explained by the error factor. And as a researcher, we'll be happy if more is explained by the factor that we have put in on the right side, and less is explained on the basis of error. If the error is explaining almost 0% of y, that is a best model, because I'll be very successful in identifying the factors which affects y. So it is a very successful model. So which is a good model? A good model is the one wherein the more explanation of change in y is coming from change in factors that we have put in the regression model, that is x, right? And not from the error. If more explanation is coming from the error, that means there is a specification error in my model. So what is a specification error? Model specification error. The model specification error is about the fact that the researcher has not been able to capture right kind of variable and put it on the right hand side, which explains why. And that's why more explanation is coming from the error rather than the regression, right? So the total change in y, that is dependent variable, can be called the total sum of a square. If you actually explain it in terms of ANOVA, it will be called the total sum of a square, right? And total sum of a square, that is TSS, has divided into two parts. One is called the regression sum of a square, that is RSS. The regression sum of a square is the one which is coming from the regression, that is the model that you have created. So it comes from the model that you have created. And the second part is called the ESS, that is error sum of a square. The error sum of a square actually comes from E, the part which is explained by E. So the total sum of a square is the total explanation, is divided into partly which is coming from the regression and partly which is coming from the error. So that's how the regression is to be looked at. And therefore TSS is going to be equal to RSS plus ESS. So if we add RSS, the regression sum of a square, and the error sum of a square, it should be equal to total sum of a square. And if you divide both sides by total sum of a square, so total sum of a square divided by total sum of a square is equal to RSS by TSS and ESS by TSS. So we are dividing TSS on both sides, right? So this TSS by TSS becomes 1. And the RSS by TSS actually reflects or tells us the ratio of explanation which is coming from regression, and ESS by TSS is explaining the ratio of explanation which is coming from error, right? So these two ratio. So this particular ratio RSS by TSS is called R square. So there is a concept in regression called R square. So R square is calculated based on this formula, RSS by TSS. So R square is called the coefficient of determination, and 1 minus R square, which is ESS by TSS, is called coefficient of non-determination. So what does this coefficient of determination, that is R square, means? R square means that this is the percentage of explanation which actually comes from the regression. And 1 minus R square means this is the percentage of explanation which is not coming from the regression, it is coming from the error, right? And therefore, if you have the percentage of explanation higher, like 70%, 80%, 90%, if R square is, let's say, 90%, it's a good R square, very strong R square, and we should be happy about that. So higher the R square, the better the regression model is, and the researchers should be happy about that. And higher the 1 minus R square, it's a problematic equation, because there may be a specification error. We have not been able to capture the right variable, so that can be one reason. So there is something called model fit, and the model fit is about the fact, what is your R square? Is it higher, or it is lower, or is it moderate? So if a high R square, that is 0.7, 8, 0.8, 0.9, you get like 90%, 95%, 98% explanation that is coming from regression, is called a better fit. So goodness of fit, the model fit, is actually measured on the base of R square. And these are the figures I have put in over here. I'll get back to this figure after the calculation. I'll show you by using the data, because I have taken it from that data. So I'm fetching a new data for doing the regression in front of you. Okay, let me just open the data. So I'm taking this policing time regression data. This is the data in front of us. We're going to use regression over here. So what it says is that this company is actually preparing different kind of glassware: bowl, casserole, dish, tray, plate. These are the coding for the different types of glassware that is being manufactured. This is the data for the diameter of the product. The diameters are, some of the products are bigger, some of the products are smaller. So these are the diameters, and this is the time which is actually taken for polishing the product. So these are the time data which is required for polishing the product. So here we are interested in knowing how do we model time based on the diameter, because time actually is going to be determined on the basis of the fact that what is the size of the product. So we have a regression, we go to regression, we go to linear regression. So, and then our dependent variable is time, because we want to model time based on the diameter. So we are taking one single model, diameter, time and diameter. So we go to statistics. So it's already checked here, estimates, give us the estimates, give us the model fit. So we don't want anything else other than that. Plotting, we don't want right now, we'll do it a little later. Here, the predicted value or residuals, I'll show you these residuals again later on. So first we'll talk about the basic information or basic data output that we get from regression. So here we have the model summary table. Now in model summary table, you can see that the R is 0.7, 0.7 is the R, and the R square is 0.49, and the adjusted R square is 0.482. So we'll talk about adjusted R square later. First, we talk about this R. R is the simple correlation between the two variables. So R means correlation. So it is a simple correlation. And R square is R into R. That means correlation is squared up. right? So when you square up the correlation, that is 0.7 multiplied by 0.7 is going to give you 0.49, right? So this is the R square, and I'll show you how this R square has been calculated. This is also the way to calculate R square, but in terms of the Anova table, I'll explain the R square from the equation that I showed you previously. Now, the question here I'm asking is, because we are dealing with a simple regression, that is one single variable model, which one are we going to use to determine whether the model is good or model is not good, is a fit or not fit? R square or adjusted R square? Which one are we doing?
R square.
Adjusted R square.
Who said adjusted? Somebody said adjusted R square?
Yes, sir. It's Kumar Saurabh, sir.
Kumar, adjusted R square. So why do you think we use adjusted R square here?
So it's being adjusted against the degree of freedom.
Being adjusted against the degree of freedom. Very good answer. It's a right answer. But for single regression equation, that is simple regression model, that is one single variable that you have on the right hand side, we are not going to use adjusted R square. We are going to use R square. But the definition of adjusted R square is correct, what Kumar Saurabh has said. Now, the reason is that in single regression equation model, your t-test and the f-test actually converges, and they actually convey the same thing. So you don't have to differentiate between the f-test and the t-test, right? And the value of f is equal to t square. That is what happens. I'll show you that. And therefore, you have a limited degree of freedom here. So it is not affecting your model fit. The more the variable you add on the right hand side, it is likely to affect your R square. Because if you, let's say, if you keep 50 variable on the right hand side, so कोई ना कोई तो y को affect करेगा ही करेगा. 50 मैंने डाल दिए, अब वो सेंस बनता है नहीं बनता है बात की चीज है, लेकिन 50 मैंने डाल दिए तो आर स्क्वायर मेरा ऑटोमेटिकली ऊपर चला जाए, तो कोई ना कोई तो कहीं ना कहीं से उसको इन्फ्लुएंस कर ही देगा. So this is not the right reflection. R square is not the right reflection in that case. So you have to adjust it for the degree of freedom, because you are enjoying greater degree of freedom by adding more variable on the right hand side. That is the logic why we are using adjusted R square in the multiple regression, not in the simple regression. Is that clear, Kumar Saurabh?
Right, sir. Thank you, sir.
Okay. Fine. So now we are going to Anova table. Anova table is about the f-test. You can see here, f statistics is calculated over here, and you can see sum of a square, is given. These are the sum of a square. Regression sum of a square is 1,287.173. Residual sum of a square is 1,687.511. And the total sum of a square is the addition of these two, so which is 2,974. This is how it has been calculated. Degree of freedom, we all know how to calculate degree of freedom. So I'll get back to degree of freedom in a while. So you just remember these kind of figures, and let's go back to my PPT. If you look at here, so what I have put is regression sum of a square value. I have put here 10287 was the roughly the regression sum of a square value. And error sum of a square, residual sum of a square value was 10687. I have taken it from that table, right? Divided by the total sum of a square. The total sum of a square was 2,974. So 2,974 here, 2,974 here. If you divide 1,287 with 2,974, what you get is 0.49. So you can calculate and see. So I'm going back to the data again to show you that. So if you look at 1,287 is the regression sum of a square, divided by the total sum of a square is 2,974. So you can check that. If you divide 1,287 with 2,974, you will get 0.49. So that's how the R square is calculated. Right. Similarly, if you look at the how the 1 minus R square is calculated. So 1,687, which is the error sum of a square, divided by the total sum of square. So the ratio comes to 0.51. And if you add this 0.495, 0.51 is equal to 1. So, the total sum of a square is divided into two components. regression sum of square, other is error sum of square, right? The ratio of error sum, regression sum of a square is called R square, and the ratio of error sum of a square with the total sum of square is called 1 minus R square, which is coefficient of non-determination. So here in this model, the interpretation is that the variables that we have kept on the right hand side, they are explaining 49% of variations or changes occurring in my dependent variable, that is y. So if the total change occurring in y is 100%, let's say, so 49% is explained by my variable that I have kept in my model, and 51% is actually coming from error, which I don't know how it is happening, which all factors are affecting it, I don't know, but it is getting affected by several factors, which is clubbed under E. So is this a good model or is not a good model?
We have to check another variable because the percentage of error variable is greater than the current variable. So we need to introduce another one, but we can consider it as a good model because the significance of F is 0.00%. So it is considered as a good model. F is significant, T is also significant.
So we'll say it's not a very strong model, but it's usable. Is that
Yes,
okay?
sir. Yes, sir.
It is usable because F test is significant.
Yes,
and the variable, if you look at the coefficient table, the beta is also significant. And that's
but
why
there
it
is
is
a scope. There is a scope of another variable to be introduced.
Absolutely, no doubt. So specification, we have to go back and check this specification. So this is very clear from this model. Very nice. So the degree of freedom. So anyone what is degree of freedom, by the way? Any of you? So degree of freedom is actually it plays a very important role. In statistics, one of the preoccupation dealing with the numerical data is that the data should be normally distributed. And when we collect the data from sample, because this data is also collected as a sample. So sample data will have the problem. It may or may not be normally distributed. So if it is not normally distributed, then we have the estimations, whatever we get, may get inflated, or we may not get the right kind of results. And therefore, in order to achieve the degree, the normality in distribution, the degree of freedom comes as a statistical compensation for that. So what happens in the degree of freedom is that if suppose you are given with 2,000 rupees and you want to, or you are asked to distribute it to 5 people, you have the choice how much you're going to give to the first, to the second, to the third, to the fourth. And when it comes to the 5th person, you lose the freedom of distribution because your total has to be 2,000. So total is working as one constraint on achieving the normality of distribution. Because in the 5th case, you don't have the choice. Whatever is left, you have to give it to the 5th person because your total has to be 2,000. You cannot distribute more than 2,000 or less than 2,000. But again, if I put one more constraint into it, I say, okay, you distribute it in such a way that your average becomes 1,800. So your total has to be 2,000 and average has to be 1,800. What will you do? Your freedom will be lost further, and it will be much more difficult for you to achieve the normal distribution. If I add one more constraint into it, I'll say, okay, you distribute in such a way this 2,000 rupees to 5 people that your standard deviation should be about 2.5. So if I put another constraint in terms of a standard deviation, you have more difficulty in achieving the normal distribution. So more the constraint that you feel that you have, the greater is the chances that you are unlikely to achieve the normal distribution. So degree of freedom is a kind of compensation. It's called the statistical compensation, which is given to the scholar, to the data at hand for your inability to achieve the normal distribution. So that's the simple way we can look at the degree of freedom. The formula that we calculate is in the regression. The degree of freedom is 1. That means you have the 2 variable, 1 independent, 1 independent, and 2 minus 1 is your degree of freedom. The other, that is 57 degree of freedom, is calculated on the basis of the number of observations that you have. So there are 58 observations, so 58 minus 1 is your observation. So there are many ways to calculate degree of freedom. Somewhere the degree of freedom is calculated row minus 1, the column minus 1 multiplied, these two multiplied together is the degree of freedom. In attributes, we calculate like that. So here, the mean square is calculated based on the sum of a square divided by degree of freedom. So you can see here, 10287 divided by 1 is going to give you 10287. So that's how it is calculated. 10687, that is the sum of a square divided by 57 is going to give you 187. So that's how it is calculated. So mean square is calculated by dividing the sum of a square with the degree of freedom. Now, how this F is calculated is dividing the first figure with the second figure. So that is 10287 divided by 187 is going to give you 54. So 54 is your F. What is that we actually look at in F test? So what is this F test is all about? Anyone who can throw some light on F test? Why do we use it? What is it? All right. So F test is about the fact where we measure or where we look into the hypothesis whether at least one of the variables that you have used in your regression is significant. Yes, so if your regression has got, let's say, 5 variables on the right hand side, and if at least one of them is going to be significant or works out to be significant, then your F test is going to be significant. This means the F test is telling us whether the regression in front of you is usable or not usable, right? So if your F test is insignificant, you should reject the regression straight away, and you say, okay, this regression is useless because not a single factor is significant in this regression, so it should be rejected, right? So that is the first condition of using the regression, that the F test has to be significant. But in a single regression model, as I said, because we don't have many variables on the right hand side, there is only one variable on the right hand side. The F test actually becomes the T test. And the F test and the T test are the same. So I will talk about T test in a while, and I'll tell you how the F test and T test are the same. If there's any question, have I made the point clear to you?
Yes, sir.
Yeah. Okay. So let's go down to the coefficient table. Right. So when we look at the coefficient table, you can see here constant. Constant means beta 0, the value of beta 0, and diameter is the value of beta 1, that is the slope, right? So here there are two kinds of coefficient that is given. One is called the unstandardized coefficient, another is called the standardized coefficient. So question to you, if we have to take the coefficient from here in order to ascertain our regression equation, which one would you like to use, unstandardized coefficient or standardized coefficient?
Unstandardized.
Ah, fantastic. Very good. Can you explain a little more why standardized coefficients are not used?
सर इक्वेशन में हमें उसमें वो ज्यादा एक्सप्लेन करते हैं, क्योंकि अगर हमने डेटा हमारा स्ट्रक्चर्ड होगा तो वो प्री डिफाइंड होगा, इसलिए हम अनस्टैंडर्डाइज्ड यूज करते हैं टू डिफाइन द रिलेशनशिप बिटवीन द वेरिएबल्स, और टी टेस्ट को वो ज्यादा अच्छे से एक्सप्लेन करता है कि कौन सा वेरिएबल उसमें से मोर परफेक्टली सिग्निफिकेंट है, क्योंकि यहाँ पे हमने अभी वन वेरिएबल लिया है, इसलिए हमें एक ही का वो शो कर रहा है.
ओके.
अदरवाइज फिर हमें पता चलता कि कौन सा वेरिएबल ज्यादा क्लोज है सिग्निफिकेंस के उसके.
Okay. Anyone who has done MSc statistics here? I want you to define in statistics, how do we define a standardized value? What is a standardized value in statistics? Okay, so let me ask this question in another way. You will all now be able to relate it. What is Z value? All right, so when data is actually not so much normally distributed, you convert this data into Z value. And when you convert this data into Z value, it actually gives you perfectly distributed, normally distributed data. And it makes the data look like perfectly distributed. Why? Because the Z value is calculated on the basis of the characteristics, like the whole distribution will have the mean, which is equal to 0, which will fall exactly in the middle, and 0 mean. And on both sides, the distribution will be, very, very highly symmetrical, with the standard deviation equal to 1. So any series which is converted into Z score will have 0 mean and standard deviation which is equal to 1. And therefore, it will actually gives you the perfect symmetry, a perfect bell-shaped curve. So that's what the Z score is all about. So when you convert the data into Z score and then calculate the regression, this will give you a standardized coefficient because it has been calculated from the standardized score. Do you get the point? Okay, so let me show you this. Probably you will understand it better. So here, the standardized coefficient, beta coefficient is how much? 0.7, right? 0.7, you can see it here in the table. So if I convert the data into a standardized score and then calculate the coefficient, then the coefficient should be 0.7. Is that right? Yeah, any response from your side?
Yes, sir.
So yeah, so let me convert the data into standardized value. So I have the time and I have the diameter. These are the two data. So I have checked this box, save a standardized value as variable. And then I'm saying, okay. And if I go to my data set, you can see here the two columns have been added. One is called the Z time and another is called the Z time trimester. So the time, Z diameter. So these are the standardized scores. So these are the Z scores. So it has been converted now into Z score. So I'm now going to analyze regression, linear, and then I'm resetting, and then I'm saying, okay, fine. So I'm using Z score, Z time, and then I'm using Z diameter. So I'm running the regression now on Z score, and I'm saying, okay. Look at the coefficient. Both sides, on standardized side and unstandardized side, both sides, the beta coefficient is 0.7. Did you see that? Yeah. And therefore, if we go back to our original calculation, here you see a standardized coefficient beta is 0.7, right? So, and this is the reason why we do not use a standardized coefficient, because standardized coefficients are calculated based on Z score, right? That's number one. And it has limitations. Limitations in the sense that you cannot actually predict based on Z score. And one of the purpose of regression is prediction, to find out the direction of change and prediction. So if you're not able to do the right predictions using Z score, then what is the fun in using regression? That's why we do not use standardized score. But which is the case where we use standardized regression, standardized coefficient? There are situations where you can use standardized coefficient. For example, on the right hand side, you have got 3-4 variables, and the measurement level of these 4 variables are very different. For example, one variable is kilometer, another variable is rupees, and the third variable is, let's say, in liters, liters or some other unit. So you have different units. If you run the simple regression equation, these units are not comparable, right? And therefore, any interpretation of regression is going to be wrong. And so you need to actually convert these into Z score in order to make it comparable. So that is where you use the standardized regression. So what we are going to use is unstandardized regression coefficient. And how do we, how is our regression equation going to look like? Let me give you the regression equation. So your reporting of the regression equation is going to be time is y, in place of y, we are going to write time. Time is equal to minus 1.955, which is the constant value, and 3.457 was the beta value diameter. So this is our regression equation. And here you also have to report two things. One is the t value and the p value. So I have taken this t and p value from the regression. So let me just show you those values. So here for the diameter, 3.457 is the beta coefficient, and the t value is 7.407, and the significance value, p value, is 0.000. Why it is necessary to do this t-test for the beta? The t-test for the beta is very important, because after all, this beta has been calculated based on the sample. So it is very important for us to ascertain that if I change my sample, will I get the same beta? So that's very important question. So we'll have to look at the significance of that beta. And significance, the p-value says 0.000. This means if I change my sample here in this case, I'm likely to get almost the same beta. I'm likely to get the same beta, right? So that means it's usable, it's significant. So if the beta is significant, then what will happen? We are going to reject the null hypothesis. Here, the null hypothesis is that the beta is equal to 0, and the alternative hypothesis is that the beta is not equal to 0. So here, in this case, if the p-value is less than 0.05, which is very good here, almost negligible, 0.000. So that means we are rejecting the null hypothesis and accepting the alternative. This means beta is significant. So when we say beta is statistically significant, this means we have rejected the null hypothesis. This also means that if I change my sample, then I'm going to get the same beta. So it's a valid beta. And this beta can be used for predicting the population, can safely be used for predicting the population, right? And that's why in research, it's very important that you actually look into t-test and the t-value. But as I said, if you look at the t-value, what is the t-value that you have here? The t-value is calculated based on the beta divided by standard error. So, 3.457 was the beta value divided by the standard error 0.47, you get 7.407. So that's what you're going to get. And let me just see where I've written that. So R square and adjusted R square. So I've already discussed. So you can see here the F is equal to T square. No difference between t-test and the f-test. So here your t value was 7.407, and if you multiply this, make it a square, you get 54.8636, which is the f value. So you can see here in the table, 54.865 is your f value, and that is achieved by squaring up 7.407, which was the t value for the beta, and therefore t square is equal to f, and in this case, in simple regression, single regression model, and that's why the f-test and t-test are the same. They tell us the same thing, so they are not different. But the moment you add more variable on the right-hand side, you have to have a different f-test and the t-test. These two tests are different, right? So that's how it is going to work. Is there any question so far before I discuss a little bit about this hypothesis?
So this is clear. Can you explain how to check assumptions of this linear regression?
Okay. So different assumptions. I'll proceed from here, and we'll talk about that. So if there is no question so far, let me explain a little bit on the model, on the hypothesis. So when we say null hypothesis, where from this originated, the null hypothesis? The origin of the null hypothesis is it lies in the mean model. We call it average model, the mean model. When regression was not there, we used to rely a lot on the mean model. That means that whatever is the value of x, x is stochastic, and stochastic means it's changing. And whatever is the value of x changing, what is our best prediction for y? If you don't have the regression, how do you predict that? So the best prediction was that the y is going to converge to the its mean value, right? And that is called the mean model. So if mean model is correct, then the regression equation is going to be a straight line running parallel to x-axis, which is actually equivalent to the y mean all the time. And if this is true, then your beta is going to be equal to 0, right? So this is the origin of your null hypothesis, that beta is equal to 0. That means it is confirming to the mean model. But whether your regression is giving anything different from the mean model, because in order that your regression becomes usable or it becomes useful to you, it has to give a different model or different kind of result other than the mean model. So if your regression is different from the mean model, then the beta is not going to be equal to 0. It's going to be either minus or plus in two-tail analysis, but it has to be different from the beta, different from the 0. So that's why the null hypothesis is that the beta is different from 0, and the null hypothesis, the beta is equal to 0, and the alternative is that it is not equal to 0. So once you reject the null hypothesis, then your regression becomes meaningful, and it becomes different from the conventional mean model. So that's the whole idea about it. Is that clear? Now coming back to the question which you asked about different assumptions. So let's talk about the assumption of homoscedasticity. So that's one very vital assumption that we talk while dealing with the error, because it is based on the error diagnostic, right? Because error has got a different pattern, and unless you assume something very stable about the error distribution, your regression beta is going to be inflated, or it might be giving you unreal result, which will affect your predictions. And therefore, it's very important that we look at this assumption. So one of the assumption of ordinary least square method, the OLS method on which this regression is based, the OLS, famous OLS method, the ordinary least square method. Why do we use ordinary least square? Why it is called the least square? I'll just make it clear in a while. But it's also based on certain properties. It is a best estimator available. It is a linear estimation available. It is unbiased estimator available. And that's why in short form, it is also called having the property called BLUE, B-L-U-E. So BLUE stands for best linear and unbiased estimator. So OLS is BLUE, having BLUE property, the best linear unbiased estimator. And that's why the OLS is used. So if we look at the concept of error, let's say, so the error is equal to y minus y estimated. This means the value of y that you actually have minus, if you deviate it from the estimated value of y that you get from the regression, it becomes the error. And then if you sum total, that is sigma e, means if you add up all the difference, then you get the total sum total of the error. But the problem with the y minus y estimated is that if you sum it to if you create the sum total of it, the sum total will always be equal to 0, because the regression lines, if you look at the two lines, x on y and y on x, they passes through the mean, and the sum total of minus and plus that you're going to get with this deviation is going to make it equal to 0, and therefore your sum total of the error is going to be always going to be equal to 0. So if sum total of the error is going to be 0, then what is that we are going to minimize? Our purpose is to minimize the error. So we are not minimizing y minus y estimated. So what we are minimizing is the error square. So sum total of y minus y estimated is square. So y minus y estimated square is to be minimized. And that's why it is called ordinary least square. So square means the error square. Least means the minimum. So the whole process is called minimization of error square, and that's why it is called OLS, right? So that's the idea why a square is to be minimized. So if you know the mathematics a little bit, calculus, this is just for those who understands calculus. Those who do not understand calculus, you can ignore this, and you can understand the essence of what we are talking about. So you have the first order conditions. If you differentiate y minus y mean square with the first parameter beta 0, and then again with second parameter beta 1, and make it equal to 0, you get the minimization and maximization conditions for it. And this is the process. If you minimize the first one and if you minimize the second one, you get the two normal equation. And these two normal simultaneous equation is the basis for calculating the value of beta 0 and beta 1. So any statistical textbook, if you open, you can see how it has been done. So those who are interested can go back to the textbook and understand that. So if you look at the error in total calculated, so you have the y, actual y, which is there with you, minus the estimated y. The estimated y means beta 0 plus beta 1 xy. So here I have put minus over here. So because we are deducting, because it's a minus process that we are following. So we have the in the regression that we have in front of us, time minus the estimated value 5.8545 plus 0.014 diameter. I'll check this value from the because I don't think this is correctly written over here. So let me just take out the value. So I'm just noting it down. So your regression equation is y is equal to minus 1.955 plus 3.457 multiplied by diameter. So this is the equation that we have. So let me also show you that it is written over here. So this is the time minus 1.7. If I have to calculate the error, then I have to take y minus this whole thing. And when we do the minus, this minus become plus and this plus becomes minus. So it will become y plus 1.955 minus 3.457 diameter. This is what is going to happen. So I'm going back to the data to show you how error is calculated. So I'm going to transform the data. So you can also learn another uses of another button, how it is used. I'm going to transform the data. I'm saying compute the data. So I'm manually calculating the error. So I'm saying you give me the value of error, and I'm building the argument over here. So I'm saying y is time, then I'm saying y minus y, sorry, it will be y plus, not minus, y plus 1.955, then I'm saying minus 3.457. Any question how the error is being calculated here? Okay, so when we say okay, then we look at the data set. The error is already calculated over here. You can see. So I have calculated the error manually, right? Just to give you an idea of how it looks like. So we go to analyze. We go to, let's say, regression. Go to linear. Then we go to save, right? And then we are saying, okay, residual, save, or give me residual unstandardized residual. And you understand now why we are not asking for a standardized residual, because standardized residuals are going to be based on Z score. So we don't want to use that. So unstandardized residual, and then we say, okay, then we say, okay. It has given us all the calculations along with the residual, which is calculated over here. These two figures are very different. Why? Let me go back to error again. Let me see what is the mistake we have done. Oh, this is on the Z score. Sorry. So I have to take time. Then we have to take the diameter. Then we go to save, unstandardized, continue, and then you say okay. So here you see, this is the residual error that has been calculated. So you can see 12.61, and this is the manually we calculated 12.62, 16.69, 16.69, 29.6, 29.6. So, you know, the error which is calculated by the package and the error that we have calculated manually is the same. So that's the formula for calculating the error. So that's one point. Now, second, go to graph. Then we go to chart builder, right? So we are creating a chart. So here we go to histogram. No, sorry, a scatter dot plot. We drag it on the canvas, right? It's asking which one X and which one Y. So we are saying, okay, fine. So give us the distribution of the error. So I'm saying,
Time
okay,
is Y.
Pardon?
Okay, okay. We are checking error. I'm sorry.
So we are saying, give us the distribution of the error vis-a-vis Y, right? So give us, plot the error against the Y, and then say, okay. So let me see the plotting. So here is your plotting. So if you look at this plotting of the error, so it's an error distribution, which is shown over here. So if you look at this point, the error spread is this much. Then you look at this point, the error spread is this much, and look at this point, error spread is pretty high. It has increased. And look at here, the error spread is further going up. So if you want to draw the line which covers the error, the line will go from here, and another line will go from here. So, and then if you look at the expanse of how it is going, so it is actually diverging, the two lines. This means as the value of time increases, the distribution of error actually gives us more spread or more variation. So it is not homoscedastic, right? Let me just take out that. Yeah. So assumption of homoscedasticity. So this is not, error is not equally distributed. Equal variance is not there in this, data. So this is called the problem of heteroscedasticity, right? So this is one of the violation of one of the assumptions. Now, question is, if the error is heteroscedastic, then what to do? What should we do? So this can be also because it's about the spread of the error. So this can be because of a couple of reasons. One could be, the first and foremost reason could be the presence of, we call it outlier. So you have the data set and there may be one or two outlier in that, right? So that can also cause the heteroscedastic scedasticity problem. So outliers are the data which do not actually match with the rest of the data. So one of the way to look at outlier, whether the data has outlier or not, we can go to analyze, let's say while calculating the regression, we can go to plot, not the plot. We can go to save, and then we can save these two values, the Mahal-Lewis and the Cook value. And we say, okay, so here in your original data, if you look at, they have calculated already these two values. This is a Mahalanobis value and this is the Cook value. Then you go to graph, reset, build another graph, and keep Mahalanobis value on one axis and Cook value on the other axis. You can use it any way you want. And then say OK. And look at this graph. So here what you see is that all the data are hovering around the same place except this data. So this data is a clear case of outlier, right? So, you can also look at this data as outlier, which is nearby, but it's away from the mainstream data. So this data set has got pretty good spread, and there is a presence of heavy and huge outlier. And with the other set of couple of data which are spread away from the same data. So that means the normality distribution has been compromised for this data. And that's the reason why the heteroscedastic problem occurs. So what do you do with the outlier? The only thing that you should do with the outlier is to remove it. So you have to identify your outlier and remove it. So you can just plainly, create a graph, scatter plot, and see which data is outlier, and you can remove that. That's one way. Another way is that if you don't want to remove the outlier, then you can convert the data into log data. And converting the data into log data has got several advantages. When you convert the data into logarithm, the natural log data, then it becomes more consistent, and the spread, the variations in the data actually goes down, and it goes down quite a lot. So that's another way of dealing with the outlier. So we'll have more occasion to talk about outlier, because outlier will come in multiple regression data also. So I'll show you over there. So if there is any question right now, before we move on to some other analysis.
So log data we take, then number our n, the number of observation will reduce, right?
No, why should n reduce? Because your number of observation will become the same. The only thing that will happen is that your data will be converted into log data, log
Okay.
n.
So log is different than unit root.
Yeah, absolutely.
There we will
And
take the
what you are
difference.
taking is a natural log, that is e to the power, the natural log, e to the power, not the 10 base.
Okay. And for unit root, it is different. There we are taking differential of the data.
Yeah,
of the
absolutely.
variables, independent,
Yes,
individual variables.
That is different. That is different.
Okay. For log, we will. Sorry.
Yeah, please go ahead. Please go ahead.
So for log, we have to mention that this is our L variable or log variable, or for if we are taking differential, we mention it by D.
Yeah, D is when you use the differential calculus, then you use the D.
Okay, both are different.
Yeah, dy by dx, that they're different actually. Okay. So there you actually find out the rate of change.
Okay. So could you please help us explain me this, how to take the log of the data?
Yeah, sure. I'll do that. So just see this example where double log functions have been used. So we have a data called IMP, which is a function of EXP. EXP is the expenditure, and IMP is the advertisement retention. So in advertisement retention is a function of expenditure made on advertisement. So that is the data. I'll show you the data. And the formulation that has been worked out is something like this. Let me just increase it a little bit so that you can have a better idea. So you're able to see it better? Yeah. So IMP is equal to beta 0 exp is to the power minus beta 1. So this is a non-linear curve, non-linear curve. So far we have dealt with the linear curve. So this is actually the expression for the non-linear curve. And we take log on both sides. So log IMP is equal to beta 0 minus beta 1 log exp. So it becomes double log function. So there are many functions that we can use. One of the function is double log. So double log function has the advantage that the beta, actually the slope also becomes the elasticity of the curve, right? The elasticity between the two variables. And this is the proof that I have given you. I don't know, this is a mathematical derivations. So I can send you my PPT and you can have a look at how it has been derived. But the proof is about the fact that when you calculate the elasticity measures the responsiveness of change in one variable with respect to the change in another variable. That's what elasticity measures. And in linear curve, which is a straight line, the elasticity or the responsiveness degree varies at different points. So the moment you change the point on the curve, the elasticity differs. But in a non-linear curve, the elasticity remains constant wherever you actually pinpoint on the curve. And therefore, if you take log on both sides, the slope itself actually becomes the elasticity, while in normal linear curve, the slope is not the elasticity. So you have to measure, you have to multiply the slope with the point, and then you get the elasticity. So that is the point which is proved here in this regression. So I'm just going to go back to show you the calculations with the help of data. That will be much better. So I'm going to fetch the data. Open data. So here I'm going to fetch the data from the Excel. So I'm just pointing out Excel, and then I'm saying my data is here in the data for exercise, right? And then it's asking read the variable names from the first row. I said yes, read it from the first row. The data is in sheet number 1. I said yes. What is the range of the data? So my range of the data is E3 to G24. So I know it, I have noted it down. If you want to import any data from the Excel file, you have to first open the data and read it and note down from which point to which point you want to import. Because I know the data, that's why it's easier for me to do that. So this data has been imported from the Excel file. So you can see here. So you can directly import the data from Excel file. So what is this data? The data is about the various companies. Here you can see McDonald's, Coca-Cola, Pepsi, and then the data for the impression of advertisement captured in the survey. And this is the expenditure that has been done by the company. So if you really want to look at how this data looks like, what we are talking about, we do the scatter plotting here. And then we take impression, we take expenditure, and then we are going to the, let's say, group ID point. We are also saying that, okay, why don't you show us the name of the firm? And then we say, okay. So here is the scatter plot. You can see here, so beautiful. It looks so beautiful. You can see here, Pepsi is a case where the advertisement impression retained by the people are very high. It's very, very high. It's one of the highest. And the expenditure on the advertisement done by Pepsi is lower than many companies like Ford, McDonald's, even Burger King. The advertisement expenditure made by Pepsi is very, very low. So Pepsi's ad is very effective, that means. But if you look at Coca-Cola versus Pepsi, if you look at, so Coca-Cola's advertisement retention is slightly lower than the Pepsi, but Coca-Cola is spending again far less than the Pepsi on its ad. But if you look at Burger King's, not very effective because it's able to spend even more than what Pepsi is spending, but its advertisement retention is far less. The most inefficient ad is that of Ford, where Ford is ending up spending one of the highest in the market, but its advertisement retention is one of the lowest. So, this is a glimpse of what we get from the market, right? Now we go to transform, your question that you asked. So I'm going to convert these two data into the log data. So we say, okay, fine. So give me log impression. This is the name of the data. And then I'm saying you create log for me. So I'm going to search where the log is. This is ln. You can see here the description has come. It returns the base e logarithm to the numeralplex. So you put it up, and then we say, okay, impression. You convert impression into log, natural log, and report it as log IMP. And we said, okay. Then another data I have to convert is, so we reset it, and then we'll say, okay, log expenditure. So there is another data we have to convert. So I'm again bringing the log, natural log up there and putting expenditure. So what I'm asking is that convert expenditure into log expenditure and report it as log exp, and then said, okay. So now I'm going to look at the original data set. Here, both log are calculated. Both the logs have been calculated. You can see here. Now, if I go to analyze, go to regression, go to linear, and then say, okay, log impression depends on the expenditure. Give me the regression. So this is the regression that you got with the R square is 0.58 and F significant, T significant. So you got 1.33 plus 0.613. Now this 0.613, the beta that you got is also an elasticity of expenditure that you got, advertisement expenditure elasticity. And using this elasticity, 6.613, you can actually predict the advertisement. That's one thing that you can do. Second, I'm going to show you something very interesting. So we go to, let's say, we go to linear, and then we are resetting it and then calculating from the original data, right? So from the original data, what we have calculated is this coefficient. So, this is 0.63. The beta coefficient is 0.363. Now, 363 is not the elasticity. So you cannot actually use it for in place of elasticity because it's not converted into log. So when you have the original data set, without any conversion, your interpretation is absolute. But when you convert that into log on both sides, your interpretation becomes relative. So when we say relative interpretation means you start interpreting in terms of percentage instead of the absolute number. Say, for example, here, if it is 0.363, the interpretation would be that if the expenditure is increased by 1, the impression is going to increase by 0.363, right? So that's the interpretation. If the expenditure is increased by 10, the impression is going to increase by 3.63. If the expenditure is increased by 100, then the impression is going to increase by 36.3. So that's the interpretation. But if you go back to the log interpretation, calculation of log, this is. So here the beta is 0.613. Here interpretation is that if expenditure is increased by 10%, then the impression is going to increase by 0.6%. If the expenditure is increased by 100%, then the expenditure impression is going to increase by 61%. So that is the interpretation over here. So it's a relative interpretation when you use the log on both sides. And
So
it's an
when we have to
absolute-
take the log,
when we have to take the log. So there are two ways. One is in order to rectify the serious problem of heteroscedasticity, you should use log. That's one condition. Second, it depends on the objective of your study. If I want to calculate expenditure elasticity, let's say advertisement elasticity in this case, then I will actually resort to log and calculate this, because there is a purpose behind it. So there are different functions, different kind of curves which you can use for a different purpose. So that's how it is purpose driven. So sometimes what happens, the researchers actually uses different functional forms. So they will use the linear form, they will use semi-log, double log, quadratic equation. They will also use the something called the inverse function. So there are many forms the equation can take place, and every form has got its own characteristics and the context in which it can be used. So it depends on what is that you are dealing with. So it depends on that. Say, for example, here in this case, I would like to go for double log because I have a purpose to serve, because I want to calculate the expenditure elasticity. So that's how it works. But generally, the log conversion can also be done to rectify the problem of heteroscedasticity. All right, so can we stop here for lunch? When should we come back after lunch? We'll start from the same point we left. So I'll give you some more interpretation and then move on to multiple regression and dummy regression in the last session. Yeah, when should we come back? Hello, anyone? What is the duration of the lunch?
so as per the next schedule, it is 2:30 to 4:30.
2:30. So let's come back at 2:30 then.
Okay, sir.
Is that okay?
Okay, sir.
All right, good. So we are breaking for the lunch, all the participants, and we'll come back at 2:30. Is that okay?
Okay, sir. Okay, sir.
And if you have more questions, you bring in. We'll start from the same point.
Sure, sir. Thank you.
Okay.
Thank you, sir.
हाँ, कॉल किया था क्या? बोलिए। अच्छा, ओके, आपका कॉल है वो। मैंने सोचा शायद रितेश का कॉल है। आ जाइए। खाना लगा दो। आइए।
Prabhat sir.
Hello, yes, I'm here.
Okay.
आपका ओके सॉरी सो वो आवाज जा रही है शायद है ना लेट मी म्यूट So this looks like this. So you were not there. We completed the session and
Okay,
you know,
sir.
we
Sir,
declared the
actually,
lunch.
some issue with my volume was there. I was
Okay.
not getting your voice. Okay, sir.
Oh, acha. No problem. So we declared lunch, and participant told me that we have to come back by 2:30. So we'll be back by 2:30.
Okay, sir. Okay, done, sir. No issue.
Okay. So it's a
We-
lunch time now.
Okay, we will meet at 2:30. Okay, sir.
Yeah, sure.